Hello everyone, welcome to another video called Quantum Field Theory. In today's video, we'll be starting our new series on interactions. So let's begin. So we've seen what are called free fields in quantum field theory. We talked about the free scalar field, the free spinor field, even the free gauge field. Now the Lagrangian for the free scalar field is what's in the yellow right over here. And this Lagrangian implies the Klein-Gordon equation, which is this equation right over here. Now, why do we call this a free field? What does that even mean? Well, we can solve this equation pretty easily. It's a homogeneous differential equation. And the solution is the sum of plane waves. That's the general solution to this equation. For an interacting field, the field was going to interact with itself, which sounds redundant, but it's going to make sense, trust me. So to describe interactions, we add what's called a potential to our Lagrangian. And this potential is going to be some sort of function of phi. It might be phi to the third, phi to the fourth, 2 phi to the third plus phi, just some general function of phi. We add that to our Lagrangian. And we call this the interaction term. So let's put this Lagrangian into the orbital Lagrange equations and see what we get as a result. And we can see that v of phi is only a function of phi. It does not depend on partial mu phi. So when this derivative goes inside of these brackets, here we're going to have partial mu phi as a result. But here we're going to have 0 since partial of v of phi with respect to partial mu phi is going to be 0. So this part is still going to be partial mu phi, or actually it's going to be an upstairs mu. Now what about partial L over partial phi? Well, that's going to be partial over partial phi. Now again, when this goes in here, we're going to have m squared phi once we take this derivative. And then when this derivative goes here, we're going to have partial v of phi with respect to phi. So basically, this means that this part is going to be partial mu phi, and this part's going to be m squared phi plus v dash of phi, where v dash phi is just defined as being the derivative of our potential. So as a result, our new Klein-Gordon equation becomes this right over here. And we call this the interacting Klein-Gordon equation. Before, we had that this was 0. So when our potential was 0, we had this. And so this was a free Klein-Gordon equation. But now that we have the potential, what's going to happen is that we're going to have functions on this side of the equation. We can no longer just decompose it into plane waves. Instead, phi is going to be a complicated function. So how do we actually solve this interacting Klein-Gordon equation? Well, to do that, we have to use what are called green functions. So say we have this differential equation right over here. This describes a particle that is attached to a string with some external force acting on it. So you know that via Hooke's law, that for a particle attached to a spring, that ma will equal minus kx. What if we have another force acting on the particle that's time dependent? As a result, this means that the motion of the particle will be described with this equation right over here. So we know how to solve this equation if f of t is 0. But if it's non-zero, it becomes quite complicated to solve, but not that complicated. But I wanted to show you guys the general idea so that we can apply it to quantum field theory. So we can call this side over here some differential operator, because it's a function of d over dt. And big D is acting on x of t, and it gives us out some function of t, okay? Now, to solve this kind of equation, what we want to do is expand f of t in terms of delta functions. So we know that f of t is going to be the integral of f of u delta of u minus t. This is a property of the delta functions. This is basically saying that like f of t, if you have some like graph, it can be written as a superposition of delta functions weighted by some f of u, where u is just some like variable that doesn't really matter. So we can expand f of t like this, and as a result, our differential equation becomes big D acting on x of t equals this integral right over here. Now, this can sort of motivates the form of x of t. We know that when the derivative acts on x of t, we should get this as a result. So we should be able to expand x of t into something that should contain this f of u. So what's that going to look like? Well, let's just try and expand it into this right over here. So we're just expanding x of t to some box, so you have to figure out what that's going to be, times f of u, because we get f of u as an output in this f of t over here. So if we were to actually do that, we'd have the big D acting on some box, and we have to find out what goes inside, times f of u is going to equal this over here. Now we can see clearly that in order for this to actually be true, in order for us to actually expand x of t like this means that when the derivative operator goes on the inside, note that this is going to be a constant when we look at it being evaluated with this d operator. So when this goes inside here, we're going to have f of u times big D acting on some box, which equals this over here. And this implies that big D acting on this box should equal delta of u minus t. What I'm saying here is that we want to expand x of t into something, right? And we want to find out what goes inside this box over here. And we found out that whatever goes inside the box, when it's being acted upon by the differential operator, it should give us out a delta function. And we call this a Green's function. And we use the symbol g, ut, to describe the Green's function. In other words, it's defined as being some sort of function that when acted upon by some differential operator gives us out a delta function, meaning that x of t can be written as the integral of g ut fu. And that's our solution for this differential equation. So essentially, if we have this differential equation right over here, we want to expand x of t in terms of the Green's function. And to find the Green's function, we need to actually put it into the Green's function equation that defines it. And when we find the Green's function, we can just put it directly into g of ut and then multiply that by our function of time, replace t with a u, and we can find out what x of t is going to be. So we can just apply this logic to solve the Klein-Gordon equation for an interacting field. So let's do that. So we can apply the concepts that we just talked about for the Klein-Gordon equation for interactions. So just like before, this would be the differential operator, okay? And then this over here is the analog to the f of t that we were talking about. This is the analog of the x of t that we were talking about. So again, we can just expand our field in terms of the Green's function, and we get this for the definition for the Green's function, okay? So what we have to do now to actually solve this equation is just find out what this Green function is going to be. Now, in order to actually solve this equation fully, we have to specify what v prime of phi is going to be. But we can still find out what the Green's functions are going to be. So how do we actually solve this equation right over here to find the Green's functions? Well, first, we can just expand out the delta function. So the delta function, recall that it's going to be defined as the integral. That's just like how we can write out the delta function in terms of plane waves So we can use this fact for intuition in order to find out what the Green's functions are going to be. So we have this equation over here, and in the right hand side we have this integral. So we want to find out what g of x mu y mu is going to be. We can kind of think of it as being equal to this over here divided by this term, right? Think of it as being this, since this would cancel out with this over here to give us the delta function. But we can't say that it's equal to this over here because it would be an operator, since this is an operator over here. So this isn't quite right. But we know that it probably will contain this term right over here in some form. So g of x mu y mu will be proportional to this right over here. And using this fact, let's just kind of pretend that g of x mu y mu is just equal to this over here and see what we get. So if we say that they're equal to each other, what do we get as a result? Well, by plugging this in to our formula, we can just distribute the exponential inside of here. When we take the derivative of this exponential, we would be left with a factor of minus 1k minus I k mu. If we did it again, we get another factor of minus I k mu when it goes to the inside. This integral won't really matter here because we can just move the derivative in front of the integral. So these will cancel out to minus 1. This will give us a 1. This will give us a minus 1. So we get a minus k mu term here when we put this in front, or when we evaluate this with the derivative operator, well, the second derivative operator. So essentially we get this. So we get this as our answer if we say that the Green's function is equal to the delta function. But recall that we wanted this to be equal to this right over here, right? So we wanted that to be equal to this. And we can see that to actually get it to be equal to that, we just have to divide this by minus k mu plus m squared. So basically what we did was we did a clever trick. We just assumed that we knew that it was going to be proportional to the integral. So we assumed that it was equal to the integral just for the kicks of it. And if we actually did that and plugged it in, we find out that our answer would be off by a factor of minus k mu plus m squared. So we found out that we have to divide by that to actually get the true form of the Green's function. So that's how we actually solve for the Green's function for the Klein-Gordon equation. So this means that g of x mu y mu is just going to be this over here. Alright, so note that y mu, by the way, is just some space-time point. The variable doesn't actually matter that much. It's just an intermediate kind of thing, but it's just some general other space-time point. And also, you guys might be wondering that we have a minus k mu plus m squared term right over here. Doesn't k mu equal m squared? So won't this entire thing just diverge? Well, not so fast. This integral over here, right, actually use the on-shell condition for this integral over here. This integral is over the 4 momentum. We haven't really imposed, we don't really have to impose that on-shell condition here. But technically still it can equal m squared over the integral. So what people sometimes do is subtract this by I epsilon, where epsilon is just some super small number. And also, this looks very similar to the Feynman propagator for the scalar field, if you guys remember it from my video on virtual particles. So for the video on virtual particles, we found out that the Feynman propagator, the thing that looked like this, it was actually equal to this right over here, but we had I think a minus I in front. So this means that the Feynman propagator is up to a factor of I minus I. It's actually the Green's function of the Klein Gordon equation. It's kind of like how the Illuminati sign, like, wow, it's all connected. Wow. So that's kind of telling us that the Feynman propagator is going to be involved in interactions, since with the interacting Klein Gordon equation to solve it, we did the Green's function. But what do you know? The Green's function is the Feynman propagator, sort of. So this is telling us that the Feynman propagator will play some sort of role in interactions. What exactly is that role? We'll see in the upcoming videos. So we have to address the elephant in the room over here. How do we actually solve this integral right over here? What's the actual answer to it? If we actually did some slick integration techniques, we would find out that this integral is going to be equal to e to the minus mr over 4 pi r squared. Sorry, not squared, just 4 pi r. How do we actually get this integral? Not quite sure. Skimming the solution online, you'd have to write out this in terms of the spherical volume element. So you do some change of variables techniques, but you would be able to get this answer as being the solution to the actual integral. And this is actually what's called the Yukawa potential, actually. And it's the potential for the nuclear force, right? And also this r over here is defined as being x mu minus y mu. So it's just the distance between two space-time points. M is the mass. So what's funny is that the Green's function, the actual Green's function solution, is going to be the Yukawa potential for the scalar field. And Yukawa potential, that's actually the potential for the nuclear force between the neutron and the proton. So this is kind of telling us that interactions, right, can describe forces. So that's another cool aspect. And we can see that as m approaches 0, or just when m equals 0, this means that v of r is just 1 over 4 pi r. And that's just the Coulomb potential. Well, we'd have to actually multiply by a factor of the electric charge to get the Coulomb potential. Well, the exponent always wins. So since you have an exponent on top, and since the exponent is a decay sort of exponent, that means that it's going to dominate the denominator. And as a result, you're going to have something that looks like this. So it just dies down to 0 over time. However, so this is for when m is not equal to 0. But when m approaches 0, what does happen? Well, as m approaches 0, the force, the potential doesn't die out as fast. It still dies out, but not as fast, right? But when m is actually 0, you will get just the normal Coulomb potential over here. So we get 1 over 4 pi r for when m does equal 0. So what I'm trying to actually draw in this terrible drawing is that as m approaches 0, v of r becomes more long-range. So when we have a mass term, it's still a long-range interaction, right? Never actually approaches 0, but as m gets bigger and bigger, the force will die out faster and faster. And this can be and this is actually why the nuclear force is it's not as long range as the electromagnetic force, because the potential depends on mass. So yeah, that's pretty much it for today's video. In today's video, we talked about how to find the Green's function for the Klein-Gordon equation, what the Green's function is, and some of its implications. So thanks for watching. I'll see you guys in the next video. Bye.